find, so you can kind of check your work sometimes. I'm trying to find one. Here we go. This is perfect. So what I will say is, so when I ask you to do the electron configuration, I'm just going off of what you would theoretically find, just going through, filling in these electrons in order like we would expect. So for nickel, this works out. So if you can see that on your screen, it says argon 4s2, 3d8. So that's what we expect. But I want to point out something funny. And this again goes back to why these transition metals are cool. So if you look at palladium, its electron configuration is listed as krypton. So starting with our noble gas, but then it doesn't have 5s2, it just has 4d10. And so I would not expect you to know that, right? I would expect you to write 5s2, 4d8, or excuse me, 5s2, 4d8, like we would expect. But we find, that it has some exceptions based upon the compounds it makes and what we find in actuality. So hence why it's 4d10. So I would accept either answer. Does that make sense? So you may find some oddities, especially in the transition metals and then the lanthanide actinide series. You found some more in chromium and in copper already? Now let's take a look at chromium. Yeah, chromium, that's another funny one. So its electron configuration, they have 4s1, 3d5. Again, I wouldn't expect you to write that. I would expect you to write 4s2, 3d4. Both are perfectly fine. Because again, without any additional information, I expect you to just fill it up as expected. So copper has that same thing, so it only has one electron in the s orbital. And the long and the short of why that is when we do this, we're going in order and we're just expecting that all the p orbitals are degenerate, all the d orbitals are degenerate. So I'll just put generally assume d orbitals are degenerate. So this is kind of like the Gen Chem approach. Is that in Gen Chem, right, we would find that these are all our d orbitals at the same energy level. But in reality, they actually do all sorts of funny things. So they could be like that. These are just kind of the most common arrangements. And I'm sure I'm missing a ton more. And basically, they can take any sort of configurations, but notice how they're not degenerate in reality. And so this is why you get these funky orderings. Sometimes they could drop below the s orbital. That's why you get weird exceptions. But again, I don't expect you to know the exceptions. Just appreciate them when you run into them and understand, where the discrepancy occurs from. All right, back to filling it in. Exactly. So it all goes back to crystal field splitting theory. So that's not to jump ahead, but that's what this is crystal field theory. Is basically like predicting your orbitals based off of geometry. And that's basically like a higher level course. And Cambiet's like own course of inorganic chemistry. So now let's go back to filling in our electron configuration in our expected order. So 3D, we fill up our 3D10. Now we're back to 4p. So again, make that note, because I've seen people, stick to 3p, but back to 4p. So 4p1, 4p2, 4p3, 4, 5, 6. So krypton. Now we go back. So this is n equals 5. So we have 5s1, 5s2. Now this is 4d. Now we fill up our 4ds. Back to 5p here. Fill up our p. Now back to n equals 6. This is 6s1, 6s2. Uh-oh. So now, where do we go from here? So now we have a few discrepancies again. And so first of all, let's figure out what this is. So now this is our F block. And my circle is getting very large. Oops. Knew we'd have some issues. Oh well. I'm no artist, obviously. So now we're at the n equals 4 level. So at n equals 4, we can have an s orbital, we can have a p, we can have a d. Now we have a new one called f. And so these f orbitals, these are what they look like. So they're pretty crazy looking. So, you can generally draw the d orbitals. F orbitals are a little bit more complicated. So notice that there are 7 of them. So each of them, again, is going to hold 2 electrons. And so how many total does that give you? So how many total electrons are in our f orbitals? So 2, there's 7 of them. $14 total, exactly. And so this is an important number because we're about to go over where we can find more problems, I'll say. And so actually my periodic table is funny. And let's look at why I say that it's funny. So let's count how many across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What's kind of off about that? So we have a problem. Oh, there's kind of too many across, right? So we would only expect there to be 14 across. So this is, let's label this as our F block. And so we expected 14 across. And this is where you get some discrepancies. And differences in electron configurations. So what's funny, sorry, I'm seeing how they did it. So 6s2. Because they technically call this one a D block, but there are a couple of ways to do it. So how I like to think about it is I put lanthanum and actinium here. So you could say, right, so this is 5D1 here. But this is where you get some oddities. So you could either, so for lanthanum, for example, you could do its electron configuration as xenon, 6s2, then 5d1. And that would be, acceptable because it's here in this d1 potentially. Or you might see it as just 4f1 if people put it at the start of the 4f. So again, we're in our n equals 4 for our first f block. So this is 4f and this is 5f. So 4f1, 5f. And then the thing you have to keep track of is, again, you can't go over 14. So you kind of have to figure out what you're going to do with lutetium over here. And so you could either fill it up, right? So you could go here, xenon, 6s2, and then fill in 5d1, and then 4f14. But you can get some kind of discrepancies in the middle here. So let's see. Let's see if we agree with this one, with europium. Let's look at europium together. So europium electron configuration. So going back. So let's see, I want to do europium. So let's start with our previous noble gas. So this is where you kind of have to start keeping things straight. So we have europium is element 63 here. So I know if I'm doing neutral europium, I need 63 total electrons. That's the important part to keep straight when you have these weird kind of discrepancies where you could, have a little difference. And so let's look at the possible answers for europium. So again, I'll start with xenon. So I want to be lazy. So starting with xenon, now we just fill it up in order. So xenon, now 6s2. And again, so this is where you have to make a decision. Do you want to just count this as 4f? So this would be 4f1, 2, 3, 4, 5, 6, 7. So you could count it like that. That would give you 4f7. Which is what this little guide says. Now, I would not be opposed, though, if you instead, and so let's look at the total electrons, because again, we need to double check ourselves. So xenon was element 54. So let me do some math here. So 54 plus 2 for our 2 in the S plus our 7. So it gives us 63, right? That was the number we were looking for. Exactly. So if your table has lanthanide and actinide over here, then what you may be tempted to do instead, and I would not mark you wrong for this, is you could write, xenon 6s2, and then if you're just going in order, you have lanthanide over here, so 57. So you could say that that's 5d1 over here. So this is 5d1. So we're first going to go 5d1. Now we'll go back and finish up with the F block. So then this would be 4F1, 4F2, 4F3, 4F4, 4F5, 4F6. So that's where you could get kind of a slightly different number. And again, I would not count that wrong. So 4F6. So let's just finish up labeling. And then I want to go over periodic trends really quickly before we end. So let's see. So this is back to 6p down at thallium. Then radon, so we're almost done here. This gives us our 7s block here. Now back to 6d with the actinides, which goes down to 5f. So fill that in here. Then from Lawrencian, finish up the D's. Go back to 7p over here. And so that kind of finishes it. And again, if you get confused, there are several different resources to help back you up. So again, this is an order. And then there's also this chart down here. So this shows you the general ordering as well. I like this diagram only because it gives you the difference between them. So notice your largest gap is between your 1s and your 2s orbital. And then this is also why things start to get a little funky, as you go higher, you notice that these energy levels are very close. Right? So your 4p, your 5s, your 4d, all these are really close together. So hence why you can also get some funny electron configurations. So let's go over some periodic trends. We may have to hit these again in recitation, so they're not too rushed. But let's first start with our atomic radii. So our radius, it of course increases as we go down the periodic table. So radius goes larger as we go down. Now what happens as we go across? So we didn't quite talk about this. Let's go back and kind of think about this. So let's look at neon. I want to take a deeper look at neon. So what happens? Actually, let me start a new tab. So we're looking at neon. Where's my periodic table? I just want to compare like neon versus fluorine versus oxygen here.